Hi, hello, welcome to the series on the SD card. So in this series, I'm going to talk about these SD cards and mic micro SD cards. I'm going to go talk about how they work, and we're also going to get hands-on and interface it with the microcontroller. So let's get started. Before we get started, let me just tell you what all I plan on doing on the series. So first, we're going to imagine what it would be like to get inside one of the SD cards, what it would look like. And then we're going to talk about the FAT32 file system and what file systems are, why we need them. Then we're going to plug one of the SD cards into the computer and see the insides of it, and we can see all the data, all the information. We're going to get out information from the SD card. We're going to find files, the locations of files in the SD card. We do a small side activity where we will read the information of the SD card and change the data so that a 16 GB SD card shows up as a 2 TB SD card in your system. Yeah, and then we're just gonna implement stuff with the microcontroller. So with SPI communication, we're gonna first implement a FAT32 file system, and we're gonna be able to read and write from this. And then we're going to take it one step further and implement our own file system based on top of the file system, where we interface it again with the microcontroller. So yeah, I'm going to try and keep this as simple as possible. So if you have a basic understanding of how computers work, this should be fine. I'm also want to go really in depth, so this might be quite long. We'll find out. So first part, we are going to go and look inside the SD card. So if you have watched read Magic School Bus, Magic School Bus is a kids book. It's where all these kids get into a school bus with their teacher, and the school bus is magical, so it shrinks and they go on adventures to explore space, someone's intestine, something like that. So today we are going to get into our school bus and shrink and go inside the SD card, and we're going to imagine what's going to look like. So I'm going to ask you to imagine a really big apartment building. It's rectangular and very simple. It's just a rectangular apartment building, and on each floor we have 512 rooms. Okay, and the number of floors depends on the size of the SD card. So if we have a 4 GB SD card, we will have less floors than if we had a 8 GB SD card, which will be less than, say, a 16 GB SD card, so on, so on. So the number of floors depend on the size of the SD card, but each floor has exactly 512 rooms, and each room, so one floor has 512 rooms, and one room has 8 windows. So this is what we're going to keep in mind. And yeah, this is the apartment building we have. Now we also have an elevator, and we can use this elevator to go to any floor we want. All we need to do is enter the elevator and enter the floor number. So once we enter the floor number, we can go to that floor. The challenge is to figure out which floor to go to, because it's so huge that we can't go to every single floor. If you want, let's work out how tall building is. So we'll do the math. We have a 4 GB SD card. That's 2 to the 10 raised to 32 bytes, which, since each floor has 512 rooms, and one room is 1 byte, one window is 1 bit, and one floor is going to be called one sector. So SD cards, they work in sectors. Anyway, so 4 GB has 2 raised to 32 bytes, which if we divide by 512, and we assume that each floor is of 1 meter, is 1 meter tall, then we end up with 8,608 meters tall. For reference, the Burj Khalifa is about 800 meters tall. So what we have here is probably one of the biggest buildings in the world. Now that we got an idea of the scale that we're dealing with, let's enter our room, enter the building. So we're entering the building, we're going to enter the first floor. So I'm going to start numbering with 1 and not G. So we go 1, 2, 3, 4. Easier. No G, no 0. We go into the first sector, and this is called our MBR, or Master Boot Record. This is the sector or the floor which tells us all the information about the SD card, like the size of the SD card, the version, and other information which is very important for the computer to be able to store data on the SD card. Let's imagine what one single floor will look like. So let's imagine a single floor, and I'm going to draw the floor. Like I said, each floor has 512 rooms, and each room has 8 windows. So if we take a single window, it can either be open or closed. So essentially, since it's a bit, it can either be 0 or 1. We group 8 of this together to form a byte, which I am going to call a room, and we give the byte a name. So this is what is called hexadecimal notation. If you know what it is, then you can skip ahead. Otherwise, I'm just going to briefly explain what hexadecimal notation is. It's basically you take one room which has 8 windows. 1, 2, 3, 4, 5, 6, 7, 8 windows, and each window can either be a 0 or 1. And now, because it's all zeros and ones, it's very hard to read it. So we give each distinct combination of this a specific name. So if all the bits are 0, we say 0x00. If all the bits are 1, then we say 0xff. If all 8 bits are 0, if all 8 bits are 1, then we say 0. This 0x is just a way to identify that we are talking about hexadecimal. So it goes from 0, 0 to 0, 1, 0, 2, all the way to 0, 9. Then it goes 0A, 0B, all the way to 0F. And then we go 1, 0, 1, 1, all the way till 1, 9, then till 1, 1F, then 2, 0 till 2F, until we reach FF. Okay, so now I feel like I've explained what hexadecimal notation is. Let's get back to a picture of a single floor. So I am also going to do one thing here, and I'm going to put 16 rooms in a line. So this is, say, one room. I'm going to call this 0x00. Then this is the next room, 0x01. I'm going to go up till the 16th room, which in hexadecimal is 0x0f. I'm going to put in one line, and the next one, which is the 17th position, I'm going to put 0x10. I'm going to label it. So each room has a position, and the address or the position of the room is very important. It tells us everything we need to know. So the position of this is 0x00, this is 0x0f. This is 0x1f. So if I put something called offsets here, now 01, 02, it's easier for us to, you basically have a table now, and you have rows and columns. And I said there's 512 rooms on the floor, so the last position will be 512 always. So here we have a single floor. Great. Here we have a lot of empty space, and then finally we have the last 16 tell us the last 4 partitions. So we actually start counting from the back, just for this one instance, and we say the last 16. So from ignoring the last 2, actually, you know what, it's gonna be better. I'm gonna take my SD card, I'm gonna put it into my laptop, and we're gonna open a hex editor. So, and then I'll show you it live on the hex editor and explain it there. I feel that'll be easier. But before I do, I want to talk about the hex editor because it can seem intimidating at times, especially if you're new to this. So I'm just going to explain it first, and then I'm going to show it to you. So it's essentially this table with your offsets, and it also has on this side what is essentially a notepad. Let's just think of it as a notepad. So hex editor has 2 parts. This, where the positions are given, and the actual value in each position is there. And over here we have a notepad. So here I might need to explain what ASCII is. If you know what ASCII is, you can go ahead, but ASCII is essentially just characters. It's character coding. So each character has a specific ASCII code to it. So let's say capital A has something like, so 0x is something like 0x41, a full stop has something like 0x2e, but essentially every character has an equivalent hexadecimal code. So when you open a notepad and when you save a string, let's say we say AABB in the whole notepad. What notepad does is looks at A, takes the ASCII code for it and stores it in something like that, and takes small a, stores it in the next position, and essentially does that. So if you open what the contents of the SD card is on a notepad in raw form, the notepad will take the value in the first position and try to convert it to the ASCII, which is basically English. And it might not make any sense because this was not in ASCII in the first field. This was not ASCII in the first place. So if you try converting it using ASCII convention, you're just going to get garbage. Which is why if you open Notepad, certain files look like just garbage. Like that's because this conversion is happening, an ASCII conversion is happening. Now that we are here, and I said that A is stored in the first position, A here, B here, you might be thinking, okay, great, that's it, SD card's over. If I want to store this file in the SD card, I just put it here, I store the next file, I put it here. The problem with this is now I don't know where a file starts and where a file ends. It's great because right now, for just one file, I can memorize where it is in my head. But as soon as I give this to someone else, they are not able to tell where one file starts, where it ends, information about the file, what kind of file it is. So that's why we need a file system, a way to keep everything organized to describe the data. So the file system essentially keeps things organized in it sort of acts like the contents of a book, and it also describes the data that's in it. So now that we've got into what a file system is and why we need the file system, because we need it to keep everything organized, I'm going to talk about the different file systems. So we are going to be focusing on the FAT file system, which stands for File Allocation Table. It comes in different flavors, so you have a FAT32, you have a FAT16, so on. You also have other file systems such as the NTFS, which stands for New Technology File System. The namings aren't really great. Then you have something called XFAT, which is essentially the newer version of FAT to overcome its limitations. So when we're talking about the FAT, let's assume we're talking about the FAT32. It has certain limitations such that it can only be used for storage devices of up to 2 TB. We will see why this limitation exists further in. And the file size can only be of 4 GB. So an individual file, the largest it can be is 4 GB. There are ways to get over this, but conventionally, the largest file you can put in a 32 GB FAT32 file system is a 4 GB file. So nowadays, as storage devices became bigger, this limitation became quite annoying. So that's why they came up with XFAT. So NTFS is what's used in Windows. So your Windows hard drive is all stored in NTFS. NTFS is unnecessarily complicated for storage systems like the SD card and USB drives, because they have information about the partitions, they have information of history, they have write access, read access, they have a lot more functionality which we don't need. So most storage devices like your SD card and your pen drive, they all use the FAT32 file system. So that's what we are going to be dealing with today, and we are not going to be covering XFAT or NTFS. Okay, great. So now we've figured out what file systems are, the different type of file systems, and we know that we're going to be talking about the FAT32 file system. So the first thing when you hear FAT32 is the FAT table. The FAT file system is based on the FAT table. So I said the file system has two functionalities: one, to keep everything organized, and two, to keep data about the data. So the organization is done with the help of the FAT table. So it's a file allocation table. So it's essentially just, well, a contents page. You'll have like a serial number, your name, that's the file name, the extension of the file, then the size of the file, and also very importantly the page number. But here we are talking about floor numbers because it's an apartment and the file is stored at a particular floor. So we need to figure out what that floor number is if we want to access that file. We'll get to that in a bit when I share my screen and we go into SD card. But this is essentially what a FAT table is. So we got into the ground floor, and from the ground floor we want to go to the first partition, and then we want to go find the FAT table, and then we're going to go read the FAT table, find the location of the file that we saved, and then go to that location and then see the file. So that's what we're going to do on the laptop. Just before that, I just need to explain partitions because I just said it right now. This isn't very important, but as soon as you go to the ground floor, you get into the MBR, and the MBR has a lot of information that we don't need, which the computer needs, but we really don't need all the information. We just care about the last bit of information, and the SD card can either be partitioned or not. Some SD cards are partitioned into 4, which I think is the maximum you can have on a FAT32 file system, or sometimes they're just a single partition. So my SD card is a single partition. I put it into Windows, I formatted it into FAT32 file system, and I got a single partition. And all we're going to get from here is the position of the partition. And then we go into the volume ID and we'll get into that. I feel like we have everything clear now, and now we can go ahead and get started looking inside a file, inside an SD card. Hi, welcome back. So now we are on the laptop and I have plugged my SD card in and we are going to look into it in a hex editor. So before we go through it, I'm just going to show you a few of the resources. This is the official document by Microsoft about the FAT32 file system. We are not really going to use this. We'll be using this as reference. This is a blog understanding the FAT32 file system. There are multiple blogs like this. I have saved all the links, and right now we'll be using this. You can find all of this in the description. Uh, so let's get started. So first, this is a hex editor. Uh, I can open up my disk. So disk E here is my SD card. If you can see 29.7 GB. It's a 32 GB SD card, out of which only 29.7 is usable. So if we open this, here we have all our data, and here we have the decoded text, which is essentially the notepad. And as you can see, it's divided into sectors. So we have sector 0, sector 1, sector 2, and we have here we have 62,349,312 sectors, which is, if you remember, the number of floors in our apartment building. Okay. Uh, Here we have offsets to easily refer to a single position. Uh, okay, so let's get started and let's get into the ground floor. Um, This hex editor is slightly misleading because it shows this as sector 0 while this is not actually sector 0. Uh, so for the first sector, I am going to use another software. For the first sector, I'm going to use another software called ISO Buster, which allows us to actually see the ground floor. So if I select the SD card, here you can see we have uh, you can see that these many bytes are unallocated and we have only a single partition which is of 29.73 GB. So if we open up the sector view, we can now uh, look at the actual first floor. I made a mistake and we start counting by 0, and here you can see ground floor. So most of the information here is zeros. And if I go to the blog, we can see that in the MBR, or the master boot record, which is the ground floor, most of the information here is boot code, which we don't need. All we need to see is the last two bytes are 55 and AA. And if we look here, we do see 55 and AA. So that's good. Then we see that the last 16 into 4 tell us information about the four partitions. So, like I said, this SD card only has a single partition, so we can expect partition 2, 3, and 4 to be empty. And if we look here, partition 4 is empty, partition 3 is empty, partition 2 is empty because it's all zeros, and this is partition 1. Uh, so, if we'll go further down, we want to find out this address, this LBA begin. So LBA stands for logical block addressing, which is essentially another name for is a way to call out sectors. So your sector 0 can be addressed by saying LBA equal to 0. It's just sort of the address. Now we want to find the LBA of partition 1. So from the back it is 1, 2, 3, 4, 5, 6, 7, 8. So if I go here, I go 1, One, two, three, four, five, six, seven, 8. And now these 4 bits, 4 bytes, sorry, tell me my LBA position. So we have 00200000. One thing to remember with SD cards is that you always start from the MSB. So the actual value is 00002000, and here everything is um, denoted in hexadecimal. So if we convert this, I'm just going to take out the calculator here. We have 00002000, which gives us 8192, which is going to be our first LBA block. Now if I enter that here, 192, we now come and find our LBA begin or our master volume ID for the first partition. So if you look here, what we have here is the same as what we have here, which is the volume ID of the first partition. So there is certain information encoded in the volume ID, but we can start noting down the information we have obtained from the SD card so far. So currently we got that volume ID of partition 1 is at address 8192. 8192. Okay, so we now know that the volume ID of partition 1 is at address 8192. Now we can find out all the other information here. So it tells us that the last 2 bytes should be FFAA. So now I'm just going to close ISO Buster because it's not as good a software I feel as this. So we can look here, we see that the last 2 addresses 55AA, which is sort of the boot signature to show us that we have reached the last 2 bytes of the sector. We can see that position 17 should be 02, and that is the case. We do see that. We see these bytes are supposed to be 0002, and we can see that's also true. So we know that this is we are looking at the right sector, and we can now decode all this other information such as the bytes per sector, the root directory of the first cluster, and so on. Uh, as you can see here, a lot of this information is not making any sense here, but when decoded into ASCII, but there are certain bytes which are in ASCII. That's why when they decode it, it does make sense. So going ahead, let's start by finding the bytes per sector. So this is at offset 0x0b, and it's of 16 bits, which is 2 bytes. So we need to read 2 bytes starting at 0x0b. So 0x0b is here, and if we have to read 2 bytes, it's 0002, and we read this as LSB MSB. So in the calculator, that will be 0200, which gives us 512. And we can see that the bytes per sector is 512, which is always 512. This is why I said each room on each flow has 512 rooms, always. Okay, so let's go ahead and start finding out all this information. So next we have sectors per cluster, which is of 1 byte, and it starts at 0x0d. So this is a 1 byte, and it's 40, which if we convert to decimal will give us 64. So the sectors per cluster is 64. We have 64 the sectors per cluster. So here we come across another naming, which is cluster. So we have bytes which are organized into sectors, 512 bytes in one sector, and then we have sectors which are organized into clusters. For us, 64 sectors are going to be in one cluster. This depends on the SD card, and different SD cards might have a different number of sectors in each cluster. Next, we have the number of reserved sectors, which is 2 bytes at 0x0e. So 2 bytes at 0x0e is, I'm going to read it as 048C, which is 1164. Then we have the number of FATs, uh, which is number of FAT tables, which is always 2, which is at 0x10, and it's 1 byte. So 0x10 will be here, because 1 and 0, and it's 2, the value is 2. And then we have the number of sectors per FAT. Number of sectors per FAT is at 0x24, and it's 32 bits, which is 4 bytes. So 0x24 is here, and 4 bytes is here. So if we decode this, it's 00001D BA, which is 7610. 7610. And then we have the root directory of the first cluster. This is at uh, 0x2C, and again it's 4 bytes. So 0x2C and 4 bytes tells us that it's 00000002, which tells us the value is 2. Okay, so now we have all our important information here. And if we compare it to the information given here, so if we compare the information we got with the information given here, bytes per sector always 512, we got 512. Sectors per cluster can be anywhere from 1 to 128, we have 64. Number of reserved sectors is 1164. So this depends on the SD card. So every SD card I take has a different number of reserved sectors that I've noticed. These are the number of sectors which are left blank at the beginning. And if we had to visualize it, that would look like this. So we have your volume ID, then the reserve sectors, then we have two copies of the FAT table. So you have FAT1 and FAT2. And then we have all these clusters where we store all our information. Now, now the number of fats is always 2. We got 2. Sectors per fat depends on disk size, and we got 7,610. And the root directory of the first cluster we got as 2, which is correct, and we got the signatures AA55. Now we have certain formulas which, with the information we already have, we can derive more information. So that's what we're going to do now. we are going to calculate these values. So we have, okay, so I've written down the formulas here, and now we're just going to calculate these formulas by putting in the values we already got. So first we have the fat begin LBA, which is partition begin LBA. That's this number, 8192, plus the number of reserved sectors, which we have as 1164, which will give us 8192 plus 1164, 9356, which will give us 9356. Next, we have the cluster begin LBA. So again, partition LBA plus number of reserved sectors, which is the same as this. This here, and we also need to add the number of fats, and number of fats is 2. So 2 into sectors per fat. Sectors per fat is 7610. 7610. This will give us 24576. And finally, we have the cluster LBA. So right now what we have got, this is the address of the first cluster, and each uh, you can find the next cluster by just adding 64 to this address, because we know that each cluster has 64 sectors. Now that we have the address of the first cluster, the next cluster is this plus 64, the one after that is that plus 64. One thing to note is that cluster numbers really begin with 2. So the first two clusters are not useful to us. We can't access it. And all the clusters after that we can. So if we look at cluster number 3, we enter here 3. 3 minus 2 is 1. 1 into sectors per cluster. Sectors per cluster here is 64. So 1 into 64 means whatever we got here plus 64. And if you want to find cluster number 4, 4 minus 2 is 2, 2 into 64. So you're adding 64 to that, and then we keep going until we run out of sectors and clusters. So now that we got the addresses, we can go ahead and look it up. So this is what I was talking about when I meant that we need to find the flow number, and once we find the flow number, we can go to that flow. So these are our flow numbers. One thing to note, which makes things a lot more complicated, is in this hex editor, sector 0, like I said, is not actually sector 0, but is actually sector 8192. So every sector after this is subtract. We need to subtract 8192 from it, and then we can enter it here. So I know that's a little annoying, but if we want to find the fat begin LBA, so basically the start of a fat, we can enter. We need to go to this sector, which when you subtract 8192 becomes 1164. So if I enter here 1164, here we are at our fat begin LBA. does not tell us a lot of information, as you can see. Let's go ahead and go to our first cluster, which is at 24576. Oh, like I said, it's not actually 24576. It is 24576 minus 8192, which is 16384. Here you go. So here we are at our first cluster, our cluster 0. Here we can see we have binary information, system volume, system 1, um, and after that everything is 0. We can go ahead to the next cluster, which is this value plus 64, which is 16448. And here we can see more information, but we don't have any idea of what this information means. So what we're going to do now is I'm going to open up this SD card and create a new text file here. I'm going to say this as txt find me me. Okay, so we have now stored a text file inside our SD card, and if we go back to the hex editor and open the disk again, let's go ahead to 1616448 192.168.4 16384. Here we can see that the information here is actually changed. If you can see, this is find me.txt. So this is essentially a fat table, which is sort of like a index page. So you can ignore all this information and we'll start reading from here. So the reason it's called FAT32 is because each content on the index page, or essentially each file, is saved in 32 bytes. The information about the file is saved in 32 bytes. So for this part, I'm going to be using this resource. I feel like it's easier. Okay, yeah. So the information is all here. So we can say that the file name is at 00 and it's 8 bytes long. For us, it's not at 00, but it's at 800. Well, it's there is this much information which is not very useful to us. So we start here. And we know that it's 8 bytes long. So your file name is only supposed to be uh, 8 bytes long. So that's essentially 8 characters long. If you store your file with more than 8 characters, well, then it's a different case and it's a lot more complicated. So now let's just assume that all our file names are 8 characters long, which is why I saved minus find me. So you see 1, 2, 3, 4, 5, 6, 7, 8. So this is the ASCII value of our file name, and after that we have 3 bytes of our extension. So these 3 bytes tell us the extension. That's the type of file. So here we have a txt file. After that, 1 byte is the file attribute. So this is the file attribute. Then this next 10 bytes are reserved. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and after that we have 2 bytes, which is the time created or last updated. So these 2 bytes tell us when it was last created or updated. These 2 bytes will tell us the date it was created. So we have the time, we have the date, and then we have 2 bytes, which is the starting cluster number for the file. This is the most important information we have here. So this tells us that it is at um, 000006. So the cluster number is 6. Cluster number is 6. If we want to find the address of this cluster, we can just take this 6 and put it into this formula. So we get cluster LBA of the cluster 6 is the cluster begin LBA, which is this value 24576 plus 6 minus 2 into 64, which should give us 2. Let's do 64 into 6 minus 2, which is 4, 256 plus 24576, which gives us 24832. And to see it here, we need to subtract 8192 from it. So if I subtract 8192, I get 16640. And if I go to 16640, here we can see very clearly this is the information inside find me. So we have actually gone ahead and found the file that we were looking for. This is the raw information of the file stored here. And what we can go ahead and do now is we can create another file here. We'll call this file 2, and we'll say A, B, 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 C, 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 enter. This information is inside file 2. This is the last. Now we can go ahead, go back to the, let's go back to the FAT table, which we can find at this address. There's a lot of calculation required in this. It's quite tedious that way. 8192616384. That was address for this 16384. This is our FAT table. So as you can see, this was what we were looking at before. This was file 1. Here we can see that the first byte is E5. So one thing to note, if it's E5, that means you should not look at these two lines. It's what happens when a file is deleted. Here again it starts with E5, here again starts with E5, and this doesn't start with E5. So this is our information. So you can see file 2 txt, all we are looking for is this information, which tells us that we are looking at cluster 7, which if we go here, it is, we're going to put 7 into this, and what we're going to get is this plus 64. So cluster 7, the LBA will be 24832 plus 64, which is 24896. and we need to subtract that number from it. Minus 8192.16704. And if I go here, 16704, here you go, A, B, B, and we have all the information in our file. You can see every time I put enter and I got a new line. You can see this is the character for it. This was the character for the full stop. Anyway, so what we can do now is actually edit this file over here. So what I need to do is first open this in not read only, so I can write into it. And if I go to the address, which is 16704, we can add some more information here, and let's start writing to it with, say, I'm going to write 61, which stands for AA, and I've written it. Now let's save it. You shouldn't really do this. This is not something that's quite safe for the SD card, but this is for experimental purposes only. So we save it. Now, if we go back, and now we find the file and we open the file, um, we can see that the AA has not come. This is because the file is still of 1 KB and the file knows when to start and when to stop. So what we need to edit now is the size of the file. So for that, we need to go back to the FAT address, the FAT table, which we have here. And again, doing the math, 24576 minus 8192.16384. I'm just going to write this here because I don't want to keep doing it. 16384. This is the address of our FAT table. Let's go. 16384. We can see this is file 2's information. So if you look here, you can see that file 2 is 1 KB in size, and you see the date modified, the time and the date. This, as we saw, is from these 2 bytes of information, so we can edit this to maybe change that. But what I'm more interested is in the file size. So if I go back here, the file size in bytes is the last 4 bytes. So these 4 bytes tell me the file size in bytes, which comes out to be 50, which is 80. So the file is 80 bytes long, which is not quite a bit, but which is under 1 KB. That's why this showed up as only 1 KB. What we can do now is we're going to edit this value. Let's make it, uh, let's say if we enter FF here, so we say that it's 255 bytes long. And we save it. We change the information about the SD card. Back to the file explorer and refresh this page. Well, it's still only under 1 KB, but now, sorry, this file, we can see that the AA which we added is now come into our file, even though we did not add it here. We can actually go a little more crazier, and let's just make this. Actually, let's not make it that. Let's edit this into FFs. So Now the file must be a lot bigger. Now you can see here the file shows 16384 bytes, and we have gone corrupted the file. Not so. Let's go ahead and delete this file, and let's see how it changes our FAT directory. So if I refresh this page, going back to my FAT directory 16384, you can see that now the first byte of that FAT table which we were previously looking at is E5, which is which means that it's open to be written over. It's marked as empty, and you can see this entry is also E5. This entry is also E5. These are previous files written to the SD card which has now been deleted. So they've just replaced the first byte with E5. This isn't E5, so this is find me txt, which is currently the only file here. Okay, great. So I feel like now we have got into our SD card. We were able to find out information about the SD card, edit information about the SD card, and see how it's being stored in the SD card. Hi guys, so I congratulations on reaching all the way till here and not getting bored. I hope you feel like you have learned something and you understand how the SD card and the FAT32 file system works. So let's not stop here and let's continue going further inside the SD card. So the first part of this series was very theoretical and we haven't really implemented anything. We've just understood how things work. The second part is going to be our implementation. So here we're going to use a microcontroller and an SD card. We're going to write code, embedded C code, and we are going to create our own implementation of the FAT32 file system. And after that, we are going to create our own file system on top of the FAT32 file system. So, watch part two for this exploration. Hope to see you all there.